Good morning, everybody. Let's go ahead and we'll go ahead to the agenda. First of all, a little bit of background on this presentation. This presentation is for people who are reasonably familiar with z/OS but not familiar with the communication server product. And the main focus of this presentation is communication server product itself. In other words, this isn't a presentation to teach about TCP/IP or SNA, even though I do give some basic background on it, but how we've implemented those technologies in z/OS communication server. So the agenda, we're going to start off with a high-level overview of what is communication server and how it fits into z/OS. Give a quick overview of the three networking technologies that z/OS communication server implements, which are SNA, TCP/IP, and a more recent one, RDMA and RoCE. I'll explain what those are and give a little bit of information about them. Then we'll talk about the structure of the communication server product. And also, then we'll talk about communication server configuration and operation. And finally, we'll do a little bit deeper dive into three of the main technologies the communication server implements: network connectivity, clustering, and security. Now, one of the goals of this presentation is that when you hear people talk about networking on Z, they will use certain buzzwords or acronyms that you don't hear on other platforms, so hopefully you'll understand that and be able to converse intelligently and know some of the basic principles. When I started in this product, a lot of this stuff is relatively straightforward, but because it was never explicitly explained, it took years for me to figure out what people were talking about. So the idea here is to explicitly explain some of the basic things that people who are swimming in the water already don't realize need explaining. Right, so the first thing we'll discuss is what is communication server. So the communication server name is used in IBM for products running on different platforms. There's a z/OS communication server, which is going to be our discussion. There's also a communication server for distributed that runs on P series, X series, or OEM. And we do provide communication server for z/OS, Windows, AIX, Unix, and Linux. They're distinct products. z/OS is a distinct product from the other communication servers, and that's what we're going to discuss. So within z/OS, communication server is a base element, which means it's part of the operating system. When you buy the z/OS operating system, the communication server comes with it, and it consists of TCP/IP and SNA services. Also, the communication server is the merger of two prior products, TCP/IP for VTAM, TCP/IP and VTAM for MVS. Those were separate products up until about the early 1990s, and then they were merged into the single communication server product. That history is good to know because it explains some of the structural things about communication server that may not seem to make sense otherwise. So the history is that, first of all, there was VTAM, which was the Virtual Telecommunications Access Method. It implements SNA and has been available since 1974. You've probably all heard that this is the 50th anniversary of the mainframe, but a little bit less well known is this is the 40th anniversary of VTAM and SNA. Since 1974, VTAM has been continuously implemented, and before TCP/IP came along and became the dominant networking technology, VTAM and SNA was the dominant networking technology in the data center. In the 1980s, TCP/IP became available as mainframe software. Originally, we ported the MVS software from VM, which is another operating system that runs on z/OS. I should also add, because I'm not sure how new people are, MVS is what z/OS used to be years ago. z/OS is an evolution of MVS, and MVS is the original operating system. In 1996, TCP/IP for MVS and VTAM were combined into a single product, which is communication server, and that's where we've been going forward since 1996. So I'll give a little overview of SNA technology, which people may not be as familiar with as the others. SNA stands for Systems Network Architecture. It was developed and distributed by IBM and started in 1974. So as I mentioned, this is the 40th anniversary of SNA. We also provided specifications, so a large number of other vendors could provide products to implement SNA. And SNA is a complete architecture for networking, end-to-end. It includes everything, including link protocols, node intercommunication protocols, application protocols, APIs. And VTAM used to be, SNA used to run in kind of two parts. There was VTAM, which runs on the mainframe, and then another product called NCP, which stands for Network Control Program, which ran on front-end boxes that sat in front of the mainframe. And SNA runs with three main operating systems, MVS, VM, and BSE. There's also SNA products available for Windows, but VTAM, which is the main implementer of SNA, runs on MVS, VM, and BSA. Now, SNA is a hierarchical architecture. On this slide, we're showing a picture of kind of how SNA works. It was originally strictly hierarchical. You had what we called sub-area, and that's the little bubble on the left. And with sub-area, you had type 5 nodes, type 4 nodes, and basically the higher the number of your type, the higher up you were in the hierarchy. So the type 5 node controlled all the type 4 nodes, which then controlled all the type 2 nodes underneath it. and it was all very hierarchical, and it was also very much predefined. There weren't any dynamics. Remember, this was 1974 when it first came out. So you had to predefine all of your connections. You had to predefine all of your routes. You had to lay out your network design and then put everything in system definition files. In the mid-1980s, we introduced APPN, or Advanced Peer-to-Peer Networking, and Advanced Peer-to-Peer Networking made SNA more flat and dynamic. Advanced Peer-to-Peer Networking introduced the concept of you would configure information about a specific node, and it would dynamically learn about its neighbors and learn about the rest of the network. So it made SNA a little bit more dynamic, a little bit less hierarchical, a little bit less definition bound, but there's still a lot of definitions. Then in the 1990s, we introduced high-performance routing, which was an improvement in data transport between APPN nodes. And then, key for this discussion, in 1999, we introduced Enterprise Extender. And Enterprise Extender implements high-performance routing over UDP, which means now you can do sub-area. Sub-area nodes can talk to each other across an IP network using UDP. That's probably the key technology that has kept SNA still viable today. So Enterprise Extender, like I said, allows the use of the IP network for SNA sessions. And the way we designed it, an SNA application thinks the entire IP network is just a single link, the Enterprise Extender link. And to the IP network, Enterprise Extender is just a UDP application. And the SNA traffic is actually sent as UDP diagrams over reserved ports on the IP network. Enterprise Extender was invented by us. It's supported by many platforms, including ZOS, Linux, PCOM, i5OS, which is the old ACE400, Cisco, SNA Switch supports it, Microsoft supports it. And what it does is it isolates the SNA footprints to the outside of the network. So you basically have an IP network, and on the edges of it you have these SNA legacy nodes, and they communicate with each other across the IP network using Enterprise Extender, which is SNA over UDP. So it allows the enablement of IP applications and allows you to converge your backbone on IP while still preserving your investment in SNA. One of the things that's very important on the mainframe is protecting investment. We have customers that have legacy applications that they've got a lot invested in, a lot of custom work done. They don't want to throw them out and rewrite their old SNA applications for TCP/IP. Enterprise Extender allows them to keep them while moving their network to TCP/IP. So SNA has been around for a long time, and it's been dying for a long time according to the conventional wisdom. So SNA, it's a legacy protocol, but it's still in wide use and support is still required. There's been a lot of studies done over time. For example, there's over 1 trillion lines of customer-written application code that's based on SNA applications. And a large percentage of business data is still accessed using SNA applications. I would conservatively estimate, I don't have anything to back it up, but past studies have had higher numbers than this. At least 50% of the business data in the world is probably still accessed using SNA applications. Because of Enterprise Extender, though, SNA stays kind of on the edge of the network and not visible to a lot of people, but it's there, it's very important, and it's viable. All right, next I'll do an overview of TCP/IP. TCP/IP probably doesn't need much introduction because it's basically the water we've been swimming in for the last several years in networking. But just as a quick overview, it started off as an ARPANET protocol suite that was introduced layering and virtualization in the early 70s, funded by DARPA. Later, it was developed to TCP/IP by BBN, and then Berkeley Unix on the VAX expanded it further. The code was distributed for free with Berkeley's Unix operating system, which is probably one of the things that really made it catch on. And finally, in 1983, the first BSD distribution came out, and TCP/IP has spread rapidly since then, and it is the dominant networking protocol today. And the ARPANET developed into the internet that we all know and love today. Now, the concepts of TCP/IP that are important for our purposes is layering. TCP/IP introduced layering, so there's an application layer, which is user processes cooperating with a partner on a different host. The transport layer, which is either TCP or UDP, that's how that's the layer the applications communicate with to talk to each other. And then underneath that is the internetwork layer, or the IP layer, which shields the higher level layers in the physical network architecture. And finally, a network interface layer, which is the device drivers and DLCs. This layering is key to making TCP/IP manageable. There's different products and different protocols at different layers of the network. Now, TCP/IP addressing, we're probably all familiar with TCP/IP addresses. It's 4 octets. Each octet is between 0 and 255 because it's an 8-bit binary number. But a TCP/IP address is broken up into a net ID and a host ID portion. Which part of that is network, which part of that the host can vary. We also have subnetting, which indicates what portion of the host bits are used to indicate additional networks. So this diagram shows the basic network types. If the first bit of a TCP/IP address is 0, it's a Class A network, which means the first byte is a network and the next 3 bytes are the host ID. Class B starts with binary 10. The first 2 bytes are the net ID and the second 2 bytes are the host ID. And Class C, which starts with 110 binary, the first 3 bytes are the net ID and the last byte is the host ID. Now within the host ID, an individual administrator or user can further subdivide that into a subnetwork and a host. Generally, the term subnet is used pretty universally to describe the network and the subnet together. When you talk about a subnet mask, you're talking about how many bits in the IP address represent the combination of the network and the subnet. So there's the IP addresses, and then there's ports. Right? A port is simply a single 16-bit number that identifies an application. And the way TCP/IP applications communicate is with an IP address plus a port number. The combination of those two, specify an endpoint on the TCP/IP network. So when you want to communicate with a partner, you give his IP address and his port number. That's what goes through the network and up through the layers to identify the correct partner. So we've been familiar with IP for a long time. The next evolution of IP is on the way now, which is IPv6. The version of IP that we're familiar with that uses the 4-byte octet number is called IPv4. IPv6 is the next evolution. And because one of the problems with the current IPv4 address structure is there's only a certain number of IP addresses out there, and the internet is growing. So IPv6 expanded routing and addressing by a lot. So with IPv6, the IP address space increased from 32 bits to 128 bits. And basically, there are 340 lots of billions of addresses. It's almost infinite. Matter of fact, for all practical purposes, it is infinite. One number I like to point out is that with IPv6, every atom on the Earth can have its own IP address 100 times over. So we're pretty confident that IPv6 will be sufficient for the foreseeable future. In the green boxes on the slide, we show you what an IPv4 address looks like, which you're familiar with. The second green box is what an IPv6 address looks like. Unlike IPv4, IPv6 addresses are generally written in hexadecimal. They use colons to separate every 2 bytes. And if you look in the center there, you can see double colons. Double colons mean you fill this in with zeros for as many bits as needed to get to 128. So that's just a shortened way of writing an IPv6 address. IPv6 gave us a chance to kind of do a do-over in defining IP. We learned lessons in IPv4, so we did something better with IPv6. For example, a header format is simplified to basically make the green path, or the most common case, processing packet handling quicker. It includes improved support for options. It also encodes the headers more efficiently. It allows forwarding to be more efficient. And also IPv6 offers built-in plug-and-play support. IPv6 offers the capability for interfaces to auto-configure IP addresses without operator intervention. It also allows for changes of IP addresses and makes renumbering much easier. So IPv6 has a number of improvements. IPv6 is definitely out there. It's definitely in the backbone. If you're an endpoint user, you may not see it that much because a lot of endpoints still use IPv4 and translate. But for example, if you go into a Microsoft Windows workstation and you do ipconfig, it'll show you your IPv6 address. You have one. You may not realize you're using it, but they're out there. It shows IPv4 and IPv6. So why are we going to IPv6? Because IPv4 is full, basically. There's so many IP addresses. This slide is old, and situations have actually gotten even bigger than this. This slide talks about cell phones having IP addresses like it's a big deal. Now that's pretty routine. But the Internet of Things, which is big talked about, means that a lot of things need to have IP addresses. And they basically ran out. Another thing that came along, that if that wasn't enough, is the United States government mandated that if you're going to sell networking gear to the United States government, you have to support IPv6. The U.S. government has a IPv6 profile that you have to verify that you support all the functions in it. So if you want to do business with the government, you have to support IPv6. So that's certainly driven demand. IPv4 simply isn't big enough, and IPv6 is now required to bid on IT contracts with the U.S. government. So ZeOS Communication Server supports IPv6. And the way that we support IPv6 is with a dual stack infrastructure. The diagram on this slide shows kind of at a high level how the infrastructure works. There's IPv6 on the left-hand side and IPv4 on the right-hand side. They are, from a high-level point of view, separate stacks, even though IPv4 and IPv6 can be overlaid on the same physical infrastructure. You do not have to buy new switches or routers to use IPv6. The same physical interface will have an IPv6 address and an IPv4 address. The same switches and routers will have IPv6 addresses and IPv4 addresses. The difference is really at the application layer. If the application is an IPv6 application, it can only talk to IPv6 applications over that same infrastructure. IPv4 applications can talk to other IPv4 applications. We have a common TCP and UDP transport for IPv6 and common DLC functions, and then they separate into separate DLCs, IPv6 DLC, IPv4 DLC, but they're running over the same hardware. So it's one physical network with both IPv4 and IPv6 overlaid on it, which allows the two technologies to coexist in the internet. So the next technology I'll give you a quick overview of is RDMA and RoCE. Basically, RDMA and RoCE is a newer networking technology for the mainframe, but it is something that we are going into to improve networking on Z. So it's important to understand what it is. So RDMA is a technology that allows hosts to read and write directly to each other's memory across a network without involving the CPU. So you have an RDMA network interface, or an RNIC, which basically one host sets data in a specific region of memory, pins that memory so it's not can't be swapped out, and then tells the RNIC, I want you to move this to my partner. Then the RNIC takes over and actually reads the data, moves it across the network, and the partner RNIC takes the data, writes it into the memory area that's been reserved for that purpose, and then taps the application, says you've got new data. The main advantage of this is that it bypasses TCP/IP. As far as the application and the operating system is concerned, I put the data there, I tap the RNIC, and I'm done. That saves CPU cycles, and it also saves speed. Now, one thing about System Z is customers generally pay for work by CPU cycle, right? So saving CPU cycles is always an imperative, and we're always looking for ways to be more efficient. So, as I said, data is moved directly by the RNICs, bypassing a TCP/IP stack. Now, RDMA technology is not necessarily new. If you've heard of InfiniBand is generally the technology that underlies RDMA. But unlike TCP/IP, InfiniBand is totally different. The ecosystem for InfiniBand is completely different. It requires unique hardware, unique switches, unique host application software. The networking APIs are completely different. InfiniBand is popular in the high-performance computing space, where you have tightly coupled systems that have a lot of custom software. But it is not prevalent or popular in the corporate data center because it requires a whole new network to be side by side with TCP/IP or Ethernet. Until now, a new technology has come along, RDMA over Converged Ethernet, RoCE, which we call RoCE, that now allows RDMA to run directly over the Ethernet, which means you can use your existing Ethernet fabric to do RDMA. You only need RNICs and switches that are capable of doing a few functions. So because of RoCE, RDMA is now affordable and can be prevalent in data center networks. Okay, so now let's talk a little bit about the communication server product structure. The purpose of the previous slides was just to give a background on some of the technology. We're going to revisit some of those, particularly the RDMA stuff, as we talk about specific communication server exploitation functions. So ZOS Communication Server, remember, it started off as two different products, VTAM and TCP/IP, and it still basically has two halves. It has the SNA half and the TCP/IP half. However, they're glued together into one product, and they use some common services. Network attachment, storage management, high-performance data transfer, those are all shared services between the SNA side and the TCP/IP side. So ZOS Communication Server provides TCP/IP and SNA integration. It provides Telnet 3270 support. It provides network access, internal optimizations, and enterprise extender. We also provide a suite of standard TCP/IP applications, for example, FTP, a routing daemon, Telnet, a mail daemon, and various things like that. We provide sockets APIs, and we also integrate with ZOS Unix, which is a Unix shell that runs under ZOS, so that Unix-based applications that are BSD compliant can easily be ported to ZOS, and if they're BSD compliant and sockets compliant, they can run with Communication Server. There are also a bunch of SNA applications. A lot of big middleware applications use SNA, as well as a lot of custom customer applications. Now, one of the optimizations of ZOS Communication Server, one of the things you want to avoid when you're concerned about performance is copies. So we have a Communication Storage Manager, which is a common storage manager between the SNA side and the TCP/IP side and the DLCs, so that when data comes in the DLC, it can be placed in a common area, and we just pass pointers to it up the stack instead of making copies of it as we go up and down the stack. So the Communication Storage Manager is a big part of the optimization of ZOS Communication Server. Now, ZOS Communication Server consists of SNA and TCP/IP, and the rule is each LPAR can have one VTAM. And then on top of one VTAM, you can run multiple TCP/IP stacks on a single image. So you can have one VTAM, one TCP/IP, as shown on the left there, or you can have one VTAM and multiple TCP/IPs. Now, we don't generally recommend running multiple TCP/IP stacks on a single image. There's not a whole lot of value to it, but it is supported. You can use different physical networks for SNA or TCP/IP, or you can use a single network, or you can use both. So for example, in this picture, we have an IP backbone, an SNA backbone. They're overlaid over some of the same hardware. Some of the hardware is unique. But the main thing to remember about the structure is each LPAR has one VTAM, and then within the LPAR there can be multiple TCP/IP stacks, though usually there's only one. So what about sockets APIs? Yeah, we got them. Basically every sockets API you can think of is supported on ZOS Communication Server. REX, CICS, a callable API, a C API, an assembler API. We have RPC, we have X Windows, we have SNMP. We have them provided by TCP/IP directly for MVS applications. We have them provided by LE, which is a language environment that ZOS Unix uses. So Unix applications can use them. You have a lot of APIs. The one thing I'll point out is on the far left there's a little lonely box called Pascal. We do have a Pascal API, but we don't recommend using it. It's very, very old and not enhanced. So except for Pascal, all the APIs are usable. And then underneath the APIs, you have Unix System Services, which provides a callable sockets API that our APIs interact with to do the transforms necessary. Then calls go through the Unix System Services logical file system down to the TCP/IP protocol stack. So that's a fairly conventional API picture, except we have so many APIs. So we also provide standardized applications. We provide a routing daemon. We provide electronic mail. We provide SNMP, which is a TCP/IP network management daemon. We provide FTP. We provide trivial file transfer, which is a slimmed down FTP. There's NFS, there's DFS, there's RExec, RSH. A large number of standard applications come with the ZOS Communication Server. Now, one of the technologies in ZOS Communication Server that's important is TN3270. This slide shows two ways of doing access to SNA applications. Basically, you have your SNA LU2 based application that expects to be talking to a 3270 terminal. Older people remember green screens, which are terminals that are dumb terminals that do nothing but 3270. Most people now run 3270 as an emulator, for example, communication server for Windows, PCOM for Windows is one, and there's other ones out there that emulate 3270. The top shows what the technology was in the SNA world, where you had a 3270 terminal that's used as an SNA backbone network using SNA and LU2 to talk directly to a 3270 application. But customers want to go to the bottom page where the backbone is IP, not SNA. What TN3270 does is it provides a transform. So it presents an IP face outside the box and an SNA face inside the box. So you can have a TCP/IP workstation that's running a 3270 emulator can use TCP/IP to talk to the TN3270 server, which then in the back end sets up the SNA session to the application. So this allows SNA LU2 applications to use the IP network without having to migrate their APIs. These applications, customers written payroll applications, inventory applications, they're written SNA APIs, they're old, nobody remembers how they work, the source code might be lost, customers do not want to rewrite these. So this is a technology that's introduced to allow SNA applications to continue to live over IP. IBM has PCOM and Rational Host on Demand. Those are the two products that provide 3270 emulation over IP for us, but there's other vendor products available. So the next slide shows a closer-up picture of the Telnet 3270 technology, where basically we have two Telnet servers. We have the main one, which is the TN3270, TN370E, and SNA line mode Telnet server. That's our main Telnet server that's tightly integrated with the TCP/IP stack. Then there's a Unix line mode and raw mode Telnet server that's more like the standard Telnet that you might see in a Unix world. So in TN3270, like I said, the server is integrated with the stack. This diagram shows your terminals, your TN3270 terminals, talk through TCP/IP to the TN3270 server, which then talks through VTAM to the CICS or other SNA application. Our TN3270 server is very heavyweight. It provides enterprise-class performance, reliability. We have customers that have hundreds of thousands of TN3270 sessions running at the same time through the one server. If you're using ATMs, a lot of them are actually doing 3270 under the covers. You think about a bank that has thousands of ATMs out there that can all be doing withdrawals. It's a very robust server. that needs to take those applications and get them out to the SNA middleware. So remember, there is a TCP/IP and there is a VTAM half. So we'll start off with the TCP/IP half. Obviously, you have to have a TCP/IP profile. That's the configuration file that configures the TCP/IP stack. In the TCP/IP profile, you specify your IP interfaces, things like port reservations, networking options, Sysplex related stuff. And the IP configuration reference, which is probably about a 700-page manual, provides the details and reference information. And we also provide an IP configuration guide, which gives best practices and provides recommendations and step-by-step guides to common configuration tasks. Now, where is this TCP/IP profile? It's stored in NVS datasets. You generally start the TCP/IP stack by using a started proc, which is a JCL procedure to start the thing. And there is a DD statement, a / profile DD statement that points to the file. Now, if you don't specify the profile statement, there are default places we look, but use the profile statement so that people can easily find it. Don't make them figure out what we figured out to find it. Now, the main profile also can include subfiles, so you can have your TCP/IP profile pointed to you by your profile DD statement, which then has includes in it, which allows you to do modular configuration. Our TCP/IP configuration can be dynamically changed, and this is a term that took a while to figure out. The operator command that changes the TCP/IP configuration is very obey, right? I don't know why they came up with obey for that, making the stack obey me, I guess. But a file that contains changes is called an obey file. So if an operator wants to make a change to TCP/IP configuration, they can either modify the existing TCP/IP configuration, or they can create a new TCP/IP configuration with only the changes, and then they do a very TCP/IP obey file, specify where the file is, and the changes in that file are applied to the TCP/IP stack. So when you hear people talking about very obey or obey files, that's they're talking about is dynamically changing the configuration by specifying a new configuration file and dynamically applying it. Now, to operate TCP/IP, first of all, TCP/IP provides a netstat operator command. Netstat actually runs in multiple environments. It can run as a console command, it can run in a TSO session, or it can run in the ZOS Unix shell as a Unix application. If you're familiar with networking at all, there's netstat on every platform. Windows has netstat. They all have netstat. Netstat is pretty much the standard way of displaying TCP/IP information, and we provide a huge set of displays. You can display just about anything with netstat. The device state, routing tables, connection information, stack information, and a lot of ZOS proprietary functions like Sysplex stuff is also shown in netstat, and that's documented in the IP System Administrator's command manual. Now, to control the TCP/IP stack, there is the very TCP/IP operator command. And the very TCP/IP operator command has different subcommands, including obey file to change configuration. There's also a very TCP/IP syntax check that lets you perform a syntax check on a TCP/IP profile without enacting the specified configuration. That's important on the mainframe because a mainframe running in production is a pretty key part of a customer's network. If you make a syntax change that hurts the mainframe, you probably hurt your whole business, and you're not exaggerating to say you're costing millions of dollars an hour for downtime. So by providing a syntax check, we let you run the configuration through and make sure that it's not going to blow things up before you actually apply it. And we also have a very command to control the traces. I'll go into it later. We have a lot of traces available on the mainframe. There's very start and stop to stop network resources like IP interfaces. There's very Sysplex to control the Sysplex configuration of the stack, and I'll discuss Sysplex later. Very purge cache to delete the neighbor and the ARP cache. So between the netstat command and the very TCP/IP command, you can pretty much completely operate and do pretty much anything with our TCP/IP stack. This slide shows an example of a TCP/IP netstat command. If you've done netstat route on any other platform, this should look familiar. In cases where we have netstat reports that are similar to standard netstat reports, we tried to make them look similar so people would be comfortable with them. So that's TCP/IP. VTAM is different. Remember, TCP/IP came along in the 80s and 90s. VTAM came along in the 70s. And so it shows the heritage because it's a design from the 1970s. So the way VTAM is configured is all the configuration files are stored in sys1.vtam list. That is the, I think I wrote sys on here, but I think it should be sys1. Is that right? Yeah, it's sys1.vtam list. That's a typo on the slide. And that's called the VTAM definition library. And sys1.vtam list is an MVS data set. And VTAM is controlled by using a combination of start options and configuration files. So, and it's all very particular. Start options control the configuration of VTAM itself. And they're usually specified in a specific member of the VTAM definition library that's called AT-TLS. And XX is a 2-digit number that you specify when starting VTAM. So when you start VTAM, you say list equals 01. It goes to AT-TLS01. That's where it gets the options for starting VTAM. Start options can also be configured as parameters to VTAM in your JCL, but most customers do it by files because it gets awkward to put a lot of parameters on a command line. And then there's configuration lists. Configuration lists specify the resources that VTAM controls. They're usually specified in a hierarchy of files, and the top of the hierarchy is ATC-CON-XX. And just like list, XX is a 2-digit number, so you specify config equals 01, then VTAM goes to ATC-CON-01 and starts going down those files to define its resources. And the config file, the ATC-CON-01 file, simply contains a list of other files in the VTAM definition library, and each member defines a resource that VTAM will start and control. So resources are things like application programs, physical and logical units, networking domains, etc. And it's all very hierarchical. You have you have nodes in the definition library that have nodes underneath them. The nodes underneath them, each one controls what's below it. The reference manual for this configuration is the SNA Network Implementation Guide and the SNA Resource Definition Reference. So because it's a little bit confusing, I've got a slide here that kind of shows a picture of the VTAM configuration hierarchy. So I have sys1.vtam list. Let's assume somebody started VTAM with svtam list equals 01, configuration equals 01. What happens is we go to the sys1.vtam list, find ATC-STR01, read the start options in it, and apply them to VTAM. Then we go to ATC-CON-01 because you said configure equals 01. And in that is a list of file names within the VTAM definition list. The resources defined in there are started immediately. Other resources can be started later using the operator command. So one thing that's important to point out that can be confusing is that there is a configuration interdependency between TCP/IP and VTAM when you're defining IP interfaces. Even though IP interfaces are IP, they still require some VTAM services. And that's because when we merge the products, all the DLC services are provided by VTAM. So even though TCP/IP is a stack that runs in a separate address space, the device drivers and DLCs are in VTAM. So that means when you're configuring TCP/IP interfaces, part of the definition is in VTAM. So in VTAM, you define a DLC port using what's called a Transport Resource List Entry, or TRLE. And then you define an IP interface in TCP/IP. The IP definition refers to the VTAM definition by the port name. So in this example here, I have a TCP/IP profile statement for an interface called OSA QDIO24. It says it's at IP address 100.1.1.1/24. Other IP type things like MTU, subnet mask, they would all be defined here. But port name, OSA QDI2, refers you to the VTAM list member that also uses port name, OSA QDIO2. And the VTAM list member, you provide the device driver information, the read and write channels, the data path channels, what port to use on the card. So they're interdependent. And a lot of times when you'll hear networking people talk, they'll talk about the TRLE definition. That's what that is. That's the VTAM part of the TCP/IP definition of an interface. Now, some IP interface types dynamically create their own TRLE definitions, but OSA, which is the standard one, does not. Some of the newer ones might. Some of the more dynamic ones might. So it's important to understand that interdependency. So with VTAM displays are done on the operator console using the display command, display the VTAM job name. There's a rich set of display commands similar to the TCP/IP NetStat, but it's for SNA things, documented in SNA operation. VTAM has a modify command, the modify VTAM job name command and the vary VTAM job name command. Now in general, I say in general because there are exceptions to every rule, nothing is really neat and cut and dried, but the modify command controls configuration and resources, and the vary command controls state. For example, the vary command is used to start and stop resources, and the modify command is used to change configuration information. But this is a loosely followed rule, it's only a general guideline, and all the commands are documented in the SNA operation manual. Here's an example of a VTAM display command. This is DNET EE. EE stands for Enterprise Extender, so this is showing you the Enterprise Extender information. Enterprise Extender is a very, very commonly used technology, obviously, on VTAM because that's how you do SNA over IP. All right, the next set of information is about diagnosis. Especially if you're a customer and you have a problem and you call IBM service, they're going to ask you for some of this information, so it's good to know about. So MVS or ZOS has a built-in component trace facility, and TCP/IP makes extensive use of this component trace facility. Matter of fact, we have multiple TCP/IP component traces that you might be asked for if you have a problem. There's SysTCP/IP, which is TCP/IP stack on telnet internals. Our service team often needs this because this shows us internals, what modules got called, what happened inside. SysTCP/RT is the trace for the own pre-route routing daemon. If you have routing problems, you would be asked for that trace. SysTCP/DA is the packet and the data trace. So it's not a sniffer, doesn't go over the line, but it's like an internal sniffer. It shows you the packets and data being sent. There's SysTCP/IK for the IKE daemon if you're using that, which is a little bit beyond the scope of this presentation, but I just wanted to list it. There's the TCP/RE for the resolver, which resolver is the component that interfaces with DNS to find resources in the network. It has a trace. There's SysTCP/OT, which is a trace of OSA interfaces, and others documented in IP diagnosis. Now, like I said, this is a standard MVS facility, so use MVS trace commands to control it, start and stop it, and use our parameters. Now, if you get a dump, TCP/IP also provides a large set of IPCS commands for analyzing our dumps. Those are documented in IP diagnosis. Usually, when you have a problem, you'll be asked to provide an SVC dump of TCP/IP when reporting a problem. When you provide that dump, be sure to provide both the TCP/IP and VTAM address spaces and the SData options listed there, and the CSM data spaces. The CSM data spaces are where the common data is. Remember, we use a lot of common data between TCP/IP and VTAM to avoid copies, so those data spaces need to be included as well. For VTAM, VTAM has its own trace called the VTAM internal trace. It's similar to ctrace in what's captured, and it's controlled by a trace option specified in VTAM list, but it's not a common facility. It is the VTAM internal trace. The trace data actually lives in 64-bit high common storage, and when VTAM is dumped, it's captured if CSA is specified on the dump command. If there's too much information needed that can fit into a VTAM address space, like most traces, this trace wraps. So if the trace gets too long, stuff's happening too fast, and your problem gets wrapped over, there's also the MVS generalized trace facility that writes this trace to external data sets. Now, we didn't have to provide that for ctrace because ctrace provides its own, data set writing facility. And the format of VIT trace records is documented in the SNA Diagnosis, Volume 2. And like TCP/IP, SNA provides a large set of IPCS commands for analyzing dumps, which are documented in SNA Diagnosis. Also, like TCP/IP, when you have problems, you'll be asked to provide a dump of the VTAM address space, and you should acquire it similar to how the TCP/IP dumps were described on the previous page. Communication server technology and applications. So now we're going to get a little bit more detail of kind of things communication server provides and how it provides them. So the first subsection of this is network connectivity technologies. After all, the whole purpose of ZOS communication server is connect to the network. That's what at the base it's all about. So those are some of the key technologies. And the first thing I'm going to talk about is the open systems adapter. Now this is a case where you will hear a lot of buzzwords being used that people assume that may not be explainable. So I'll try to discuss some of them. So the OSA is the open systems adapter, and it is the strategic communications device for the mainframe. If you work on other platforms, you might think it's a NIC, but it's really not a NIC. It actually includes the NIC, plus it has a built-in communication controller. And OSA is a very flexible card that is programmable to run multiple protocols. The same OSA card can run Ethernet, can run Token Ring, can run SNA, it can run a lot of different technologies. So it integrates several hardware features and supports many networking transport protocols. One of the key strengths of the OSA is it has powerful virtualization capability. And the virtualization capability is actually on board on the card, natively built in. So it allows the OSA Express adapter to be shared by all LPARs and stacks on a system, which gives economical scalability. The same OSA card can be shared by ZVM, it can be shared by Z-Linux, and ZOS LPARs. They can all share an OSA adapter. The OSA adapter includes both the NIC and the communication network controller. Now, one thing I didn't put on the slide, but I will mention, a term you'll hear mentioned a lot in reference to OSA is QDIO. And QDIO is another way, stands for Queued Direct I/O. That's the technology that OSA uses to communicate with the host itself. So when people talk about QDIO, it's often interchangeable in discussion with OSA Ethernet technology, because QDIO is how we do the Ethernet technology with OSA. So the next slide shows you some of the sharing and connectivity that OSA has, some of the terms you'll have. Here I've drawn a KEK, and the KEK has multiple LPARs. It has a ZOS LPAR, has a Linux LPAR, and then it has a ZVM LPAR, which is running multiple guests. ZVM can act as a hypervisor and run multiple guests. They're all sharing a single OSA adapter. And OSA can be shared by native LPARs, which are the two LPARs on the left, which means they have direct access to the OSA card. The OSA provides a virtual NIC, and they have an interface, and they talk directly to the OSA card. And then within a ZVM virtual machine, there is real mode and simulated mode. In real mode, which is the middle two, server C and D, ZVM basically just passes through to the OSA and lets the clients talk directly to OSA. In simulated mode, which is the two guys on the right, ZVM actually provides an internal LAN, which is called a guest LAN, and they also have what they call a vSwitch or a virtual switch, so that each guest has an interface on the virtual LAN, and then there's a single uplink port that ZVM provides, so that they think they're talking directly to the OSA adapter, but they're really on this internal network. Now, in simulated mode, ZVM provides a virtual switch and a network of virtual adapters, which it's kind of a it's kind of a link aggregation thing virtually, because we don't have link aggregation in native mode. Now, when you're doing simulated mode, some of the OSA offload functions are not supported because you're not talking directly to it. But simulated mode has other benefits. The biggest benefit of simulated mode is large scalability. Customers can and do run literally thousands of virtual servers in simulated mode, all sharing a single OSA. And also, as I said, it provides link aggregation to ZVM guests. In other words, what that means is if there are multiple OSAs on the KEC, which there usually are, customers don't like a single point of failure, so they usually have at least two. The simulated guests only have one interface, and the ZVM handles spreading the traffic across the two adapters. The people that are accessing it native or real see two different adapters and manage two different adapters. Now, OSA drivers are provided for z/OS Linux. Red Hat Enterprise Linux and SUSE Linux Enterprise Server both have OSA drivers. So it is the key connectivity technology. Now, the OSA Express adapter also is a powerful network controller. It offloads many of the tasks from the CPU. As I said earlier, saving CPU cost is important on Z. So some of the networking tasks that are processor intensive can be offloaded to the OSA. And those are address resolution protocol. Address resolution protocol is the IPv4 technology that allows, if I know an IP address, address resolution protocol maps that to a MAC address by querying. That can be offloaded to OSA. When that happens, a stack registers its local IP addresses to the OSA adapter, and the adapter responds to ARP requests on behalf of the stack. So that saves processing, but it also provides a nice value. If there are multiple OSAs attached to the same physical LAN segment and one of them fails, they know about each other, and one can take over ARP responsibility for the other, which means the failure of an OSA is completely transparent to people out in the network talking to us, because just a different OSA responds to the ARP for the same IP address. As far as the network is concerned, that IP address is still available, it just moved. OSA also offloads checksum. When checksum offload is enabled, OSA generates checksums on outgoing packets and validates checksums on incoming packets. So that saves the TCP/IP stack from having to do it, so that's a reduction in CPU cost. OSA also has segmentation offload. When segmentation offload is allowed, this is for TCP only, then segmenting TCP outbound data into individual IP packets is done by the OSA Express device instead of by the stack. So this significantly reduces the CPU cost of streaming TCP/IP workloads. The most common example of that is FTP. When you're FTPing a large file, that's a streaming workload. The OSA handles breaking it up into segments. Furthermore, OSA provides multiple input queues. This is a z/OS only value. Linux does not support this. OSA adapters can be configured to pre-sort different types of inbound traffic onto separate I/O queues to keep different types of traffic apart. For example, you have bulk data, which is FTP, and you have encrypted packets, which require processing by crypto services. Those are completely different types of service. OSA can be programmed to put them onto different queues for z/OS so that z/OS does not have to dispatch them onto the correct queue. They come to z/OS pre-sorted. That makes z/OS processing more efficient. Once again, it's CPU savings and dispatch efficiency. Okay, the next networking technology that's key for z/OS is hypersockets. Hypersockets is a unique concept to z/OS, as far as I know. OSA, while it provides a NIC and network controller, all platforms have NICs, obviously. What hypersockets is it exploits the virtualization on System Series Z, because hypersockets is within a single Z series KEC or a single Z series processor complex is an internal network that allows the different LPARs to communicate with each other internally. So we support up to 16 internal IP networks, and they interconnect z/OS, Linux on Z, VSE, ZVM, and ZVM guest operating systems, all of them within the box. So it's completely within the box, and what really happens under the covers is we do it with memory copies. So very low latency over HyperSockets. It's highly secure because there's no external cables to tap into. HyperSockets is completely internal to a hardware CAC. It's highly available because there really isn't any hardware, right? It's just copies. And cost savings, there's no external switch equipment needed. It's flexible, and it's simple to install, operate, and maintain. So HyperSockets looks like an internal LAN. It allows operating systems on the same processor complex to exchange IP traffic at virtually memory speed. So in the picture here, I show a yellow Z-series CAC, which has an OSA adapter, an OSA Express adapter, that connects to a Tier 1 HTTP server, and that connects to a firewall, which connects to a Tier 2 application server, which then connects to another firewall, which goes back to a data center in the back end. If those are all different LPARs on the same Z-series CAC, they can use HyperSockets for all those zones, which means they're running at memory speed, not using no external cables, nothing to tap into, very secure, very fast. Now the next technology I'll spend a little bit more time on because it's relatively new, and that's our RDMA implementation. The name of that implementation is Shared Memory Communications over RDMA, or SMC-R. It's a protocol that allows TCP sockets applications to transparently and autonomically exploit RDMA over a data center Ethernet network using the RoCE technology I described earlier. Now SMC-R is a hybrid solution, which means we didn't dispense with TCP completely. You start off with a TCP connection. Once the TCP connection is made, the stack negotiates over the TCP connection RDMA attributes, and if the negotiation works out, then socket data application is exchanged via RDMA rights. The TCP connection remains active as a way of controlling the SMC-R connection. Now the reason we did this model is because there's a lot of critical operational network management features that our customers need. Resilience and failover, load balancing, IP filters, connection-based security, VLANs. We can't expect our customers to throw that all away to get a faster network transport. So SMC-R integrates the best parts of IP with the performance of RDMA by using what we call a hybrid connection. Now I'll discuss that more in a second, but first of all, the requirements. To do SMC-R, you need ZOS 2.1, which GA'd last year. That's where the SMC-R protocol is encoded in software. And you also require a ZEC12 or a ZBC12. That's the generation of machine that supports it. There's a new 10 gigabit RoCE Express feature that lives in the PCIe I/O drawer. There's currently a single port enabled, and there's no virtualization of RNICs today. Each feature is dedicated to a single LPAR. Virtualization is something that's we've announced in the past that's our intention to do. It just isn't there now. We recommend configuring 2 RoCE Express features per LPAR for redundancy, because one of the things about SMC-R that is better than other RDMA technologies is we can do seamless failover between failing adapters. Most RDMA technologies require the application to manage that. You also still need OSA Express, because remember, we start off with a TCP/IP connection, then switch to an RDMA connection. So those TCP connections are done over OSA Express. That's not changed. It's a QDIO mode, and OSA can be virtualized like before. OSA, you don't really change the way you use OSA, you just put the RNICs alongside it. Now, and this kind of gets to the question I think Thomas asked. You need a standard 10 gigabit switch, or a point-to-point configuration, which means 2 RNICs wired together. You do not have to have a conversion-enhanced Ethernet capable switch. Even though RoCE stands for conversion-enhanced Ethernet, we've designed SMC-R so that the only feature it requires is global pause. And global pause is a relatively standard Ethernet switch feature. It's been around for a long time. It's got an IEEE standard. So with these, the only new hardware and the only new fabric you need is an RNIC, which you connect directly to your existing data center Ethernet, and you can do RDMA and TCP/IP over the same network. Now, because SMC-R is new, I'll spend a little bit of time talking about what it's used for and where it's valuable. Basically, what are the use cases for SMC-R and 10 gigabit RoCE Express? Well, it's mainly tiered application servers. Because today, it is our intention to make this a prevalent protocol on other platforms, but today it's only available on Z. But it is important to know we have published the specs in an informational RFC so that other platforms can implement it. But since today it's only on ZOS, we'll just talk about the cases we support today. Multiple tiered workloads like application servers talking to backends, especially for network-heavy workloads, benefit greatly from SMC-R. Transactional workloads that exchange larger messages like web services like WAS to DB2 and CICS will benefit. Streaming workloads like FTP communicating ZOS to ZOS see improvements in CPU and throughput. And any applications that use ZOS to ZOS TCP-based communications, they all benefit from SMC-R. And SMC-R is transparent to the application software. There's no changes required. You put in the RoCE card, you turn on SMC-R, and it works dynamically. So here's two slides showing some of the performance impacts. The first slide is an example of a stock trading workload. You have a Linux client talking to a WebSphere application server running a Liberty profile using TCP/IP to talk to a DB2 in the back end. The thing about this workload string is the SMC-R is only between the two ZOS systems. There's no SMC-R between the Linux and the WAS. And at the Linux system, a 40% reduction in response time was observed. So SMC-R saved so much time going between the two ZOSs that it reflected back to a 40% improvement in response time at the Linux end. The next example is FTP. Now with FTP, the bottleneck is usually not the network, it's usually the disk writes on either end. So with FTP, the main benefit you see with SMC-R is CPU savings. We do see some throughput improvements, but generally disk writes will limit that. But using SMC-R to do FTP between ZOSs save 50% of the CPU work. On the next slide, we talk about two CICS regions using a technology called IP intercommunications, or IPPN. This is a technology that allows CICS regions to make remote calls to each other across an IP network. And by inserting SMC-R into that IP network, we saw a 40% reduction in response time and a 10% CPU savings. So it got faster and cheaper, which that's sometimes a pretty hard trick to pull off. And finally, we did a WebSphere benchmark where we had two WebSphere MQ regions where we had them doing messaging between each other. By putting SMC-R in there, they got a 200% increase in messages per second. So I think these slides will show you that SMC-R, for the right workloads, has huge benefits in CPU and latency. The other thing about SMC-R, because it does TCP/IP alongside of RDMA, it preserves the existing security model. Because there's still a TCP connection, IP filters still work. Because it's at the sockets layer, connection level security like SSL, TLS, AT-TLS, they all still work. Filters work. Traffic regulation works. Because the way SMC-R works, if the TCP connection is rejected, the SMC-R connection never happens. SAF-based network resource controls like net access, stack access, they all work too because they're all below the sockets layer. Auditing based on IP addresses all works because we set up a TCP connection first. So SMC-R is designed to integrate with your existing IP network and not take away your classes of service. Now, one of the things SMC-R does is, since it bypasses TCP/IP, there are no TCP/IP packets. So security technologies that require IP packets, like IP security tunnels, do not work with SMC-R. But our stack is smart enough to know that if a technology that SMC-R doesn't support is being asked for, we don't do SMC-R. We skip it for any connections that require security technology that doesn't support SMC-R. So it's important to understand the roadmap. Right now it's only on ZOS with V2R1, so you can do ZOS to ZOS communications in the data center. IBM intends for it to be an open pervasive protocol. We have opened up the protocol, we have donated the intellectual property, and we've specified the publication to the IETF. A link to the RFC is there in the slide. Future work that we're looking at is virtualization support for the Rocky Express feature, so it can be virtualized like OSA. And we've also got a statement of direction that ZVM is going to provide guest support for Rocky devices. Okay, so we're almost to the end of this section. We've talked about the major TCP/IP data link controls. We've talked about OSA. We've talked about HyperSockets. We've talked about Rocky. There are a lot of other MVS data link controls, TCP/IP data link controls I'm not going to talk about. They're legacy. They're older. CTC, MPC CTC, LCS, same host. Those are used, for direct connections and for some specialized cases. And there's a whole bunch of legacy ones: CDLC, CLAW, Hyperchannel. Those are being removed. This slide says they're legacy, not recommended, but since I wrote the slide, we put out a statement of direction that V2R1 is the last release where these legacy types are going to be supported. So in V2R2, CDLC, CLAW, Hyperchannel, MPC, OSA, those are going to be removed from the product in V2R2. So they're definitely not recommended. OSA, HyperSockets, and Rocky, those are the strategic DLC types. SNA provides multiple data link controls. CDLC, LSA, those are all, if you're familiar with the SNA world, those are all still there. Removal of some IP DLCs does not affect SNA. Okay, all right, let's move on to clustering technologies. We talk about network connectivity, which is obviously that's one of the first things you think about when you think about a communication server product, but we also provide a lot of other technologies that are of value. And one of the things I want to talk about is clustering, because that's a unique value on Z that Z does very well, and communication server is a big part of that. So the basic clustering technology on Z is what we call a parallel Sysplex. And a parallel Sysplex is a tightly coupled cluster of ZOS systems that cooperate to provide a single system image to the network, even though there's actually multiple machines. So ZOS systems in a parallel Sysplex, they're independent instances, and they cooperate using something called the cross-coupling facility, or XCF. So in this picture here, I have two different processor complexes, and Sysplex members can be on different LPARs in the same KEK, or they can be on different KEKs, or a combination of both. The cross-coupling facility gives them interoperability between them to share data. And a client down at the bottom wants to use application A. And application A is running multiple places in the Sysplex. I don't care where it is, because to the client, the Sysplex looks like a single host, even though in between there's a lot of stuff going on. And that's our basic clustering technology. And Sysplex provides a lot of things, including workload distribution and load balancing. So in this picture here, I'm showing a Sysplex cluster. There's a bunch of servers in the background. They're all sharing data. And there's a concept called the Sysplex distributor, which is our technology. The Sysplex distributor is the target of requests from clients. When clients send requests to the Sysplex distributor, it distributes the workload to the back-end servers based on things like availability, workload, who's busiest. We have a lot of technologies for that. So to be in a Sysplex, all the server instances provide the same basic service, which means they all must be Sysplex enabled and be able to share data across LPARs. And then in order for load balancing to work, we have to obtain information about the work that the backends are doing. So we can do workload management across a cluster. And for example, one server may not be sufficient. You might want to be able to take a server down to upload it or to upgrade it and allow the other servers to take the workload. Sysplex provides improved availability because as long as one server instance is up and running, the service is available, right? The people out in the network don't know there's only one server, or they don't know there's 10, however many. As long as somebody's up, the service is available. So individual servers and associated hardware can fail without impacting overall availability. This also enables capacity management. You can transparently add and remove server instances while the workload is live, right? And nobody in the network knows, because the Sysplex manages all of it. But all of this works by giving users a single system image. They get one target host name, which is a Sysplex distributor host, to direct requests to, and then it directs requests to the correct backends. So it provides a lot of flexibility, a lot of reliability, and a lot of capacity. So one of the concepts that goes hand in hand with Sysplex is virtual IP address. On a lot of other platforms, they make wide use of loopback addresses for a similar thing, but we've got our own concept on Z called a VIPA, or virtual IP address, which is much more powerful. And a VIPA is an IP address that is not tied to a specific physical interface. A VIPA represents a concept. A VIPA could represent a host, it could represent an application, it could represent a load balancer. Because it's not tied to an interface, VIPAs don't care about network topology. So in this picture here, I have a client says, I want to connect to VIPA number 1. The name server says, okay, VIPA number 1 is the VIPA IP address, and then the routing table tells the client to go through IP10, which is on the OSA, to get to VIPA number 1. But if IP10 fails because the OSA fails, or somebody reconfigures it, the routing table can tell them to go through IP11 and still get to the same VIPA. The idea is that the VIPAs are seen from a layer 3 routing point of view as one hop beyond all the interfaces on a host, so they're resilient to interface failures. But also, since VIPAs represent specific applications, you can give your FTP users one IP address to use, you can give your DB2 users another IP address to use, and they're tied to the applications, not to the network topology. Which also means you can move applications around and move their VIPAs with them. Which is part of the concept on the next slide. We also have the concept of a dynamic VIPA. A dynamic VIPA is a VIPA that is tied to a single port or a single application, and when that application moves, the VIPA moves with it. So they survive any outage by moving to another stack via a Sysplex function we provide called VIPA takeover. In which case, if an application instance fails, another application can pick up the workload and take over the VIPA. Now, when it fails, the existing connections are broken, but future workload gets sent to the new takeover. So in this picture here, the client is looking for 192.168.253.4. It's running on a host. When that host fails, the IP address moves to another host. The client doesn't know or care. The client is still talking to 192.168.253.4. The fact that it moved around because of outages or changes is immaterial to the client. Then when a host fails, another host can take over the VIPA, and then when the failing host comes back, it can take back its dynamic VIPA and continue the workload. So obviously, one thing you need to make this work is dynamic routing. Because if VIPAs are moving around, then you have to be able to find them. The clients address the IP addresses, but the network has to be able to find them. So OSPF is the dynamic routing protocol that's provided it's the main dynamic routing protocol. It's provided on System Z. It's implemented by the ZOS Ohm Peer daemon, which is provided with ZOS Communication Server. We also support RIP, which is another routing protocol that doesn't respond quite as quickly to changes, so OSPF is recommended. Also, dynamic VIPAs are useful for planned changes. In this picture here, the .4 address might have gone down because you took down the server to upgrade it. And once again, that's transparent to clients. They don't care because the workload moves, the dynamic VIPA moves, the work keeps going. We also have the concept of a distributed dynamic VIPA, which is slightly different. A distributed dynamic VIPA is a Sysplex concept where the Sysplex distributor advertises the VIPA address and clients connect to the VIPA address. Then the Sysplex distributor distributes that workload to back-end servers based on availability, based on load, based on who's got more capacity. And the way that works is even though the dynamic VIPA address is advertised by the Sysplex distributor, it actually exists in shadow format on all of the back-end servers. So in this case, 192.168.1.1, the Sysplex distributor advertises that to VIPA, but all the hosts in the Sysplex have that IP address. So the Sysplex distributor can forward traffic back to the back-end. So back-end servers use the address but don't advertise it. And then clients connect the distributor using the distributed to VIPA, and the distributor distributes the connection to the appropriate back-end server. So in this manner, we provide a single system image for the entire cluster that's managed by a Sysplex distributor. All right, that's clustering. And our last major topic is security technologies. Security is obviously becoming more important every day, but it's always been important in the mainframe. You don't hear about mainframes getting hacked very much because security has been emphasized, for 20, 30 years, and we continue that emphasis. So when we're talking about security, first we have to talk about what are the security objectives. Security is more than just, what's my password and keeping hackers from getting your password. There are multiple roles and objectives in security. The two main objectives are to protect the system and to protect the data in the network. And once you see those two, it should be relatively clear what's the difference. Protect the system is to protect from intrusions, protect from hacking, protect people from getting your data. Protect data in the network is encryption, keep people from intercepting your data, keep people from changing it. So this page shows a lot of technologies that we use. Starting at the very top at the application layer, we have SAF protection, which IBM's product for that is RACF, right? SAF stands for Shared Access Facility. That authenticates users and prevents unauthorized access to datasets, files, resources. That's not a communication server technology. That's a basic ZOS technology. However, there's also application-specific data technologies to protect data in the network. SNME3, there's SSH, there's various authentication. Then at the API layer, we have Kerberos and Socket Secure Layer TLS that work as extensions of the Sockets API to provide encryption and data protection of data moving in the network. Then at the TCP layer, we have SAF classes to prevent unauthorized access to TCP/IP resources. In other words, you can use RACF to prevent users from accessing certain IP addresses, accessing certain ports, things like that. We also provide intrusion detection services for the system that protect from attacks on the system. The system is advertising legitimate service, an open port for everybody to use. Hackers want to do denial of service attacks. They want to flood it. We can manage that. We can also prevent intrusions, which is people, probing you for ports. We also provide IP filtering that filters out undesirable IP traffic that helps control the system. Those are all for protecting the system. Then to protect data network, we have a unique technology on our platform I'll talk about more called AT-TLS. That's Application Transparent TLS. It's a TCP/IP stack service that provides SSL services at the TCP layer transparently to applications. IP filters, will filter traffic and require IPsec protection. And we also have IP security, which is a relatively standard technology for encryption and tunneling on the network. So our network security is policy-based. This is our general paradigm, is that you specify security policies and we implement them at a very high level. There is a product called ZOSMF, ZOS Management Facility, that provides management features for ZOS, and we have a plugin called the ZOS Configuration Assistant. I'll talk about that more in a minute. But you have a security policy administrator. The security policy administrator uses a GUI-based tool to specify security policies. For example, all FTP traffic must be encrypted with triple DES, right? All TN3270 traffic must be encrypted with triple DES. All other traffic, block it. That's an example of security policies. You specify those in our graphical user interface tool. It creates the configuration files. Then we have a daemon called the policy agent that reads those configuration files and installs the security policies into our TCP/IP stack. For example, with the security policy I just said, you would write, our configuration system would write filters that say if it's not IP traffic, if it's not TN3270 traffic, discard. Give that to the policy agent. The policy agent would install that policy into the TCP/IP stack, so the TCP/IP stack would implement the policy. This provides network security without you having to put the security in your applications. So the next slide shows a picture of what the configuration system looks like. This is a general picture. It's a GUI-based tool where you specify policies. It's a plugin to ZOSMF, which is a no-charge product that comes with ZOS for managing various things on ZOS. We configure all policy disciplines with the configuration system. We configure AT-TLS, we configure intrusion detection, we configure traffic management, we configure filters. You do it all. They're separate perspectives, but they all work similarly. And the focus is on concepts, not details. So instead of writing really intricate configuration files for the policy agent, you use the configuration system to make high-level directives. For example, all FTP traffic must be encrypted with AES, and then the GUI generates the necessary files to be installed onto the stack. So it builds and maintains the policy files. It also builds and maintains related configuration files, and it also builds and maintains JCL procs and RACF directives. So it's a complete solution for implementing security on your system. If you did hand code policy files, because you're one of those people that wants to really be down on the metal, then you want to switch the configuration assistant, we can import your policy files and convert them to the configuration assistant. You can use the configuration assistant to manage multiple stacks. We support the current ZOS release plus the past two. So if you have a Sysplex that's got a mixed level of systems, you got 2.1 systems, you got 1.13 systems, you got 1.12 systems, you can configure them all with the policy assistant. And it actively monitors the stack and imports configuration information. So another technology that we use with security is Data Power. Data Power is an appliance provider. They're front-end appliances that sit in front of your system. They provide XML transformation, but they also provide security. And we provide APIs for Data Power to talk to ZOS. So Data Power can use what we call the NSS server, which is the network security server. Data Power can act as a client to that, and using that, Data Power can access key rings. It can access security information on the host like RACF. So a user can come into a Data Power box using their ZOS user ID. Data Power can go to ZOS, look it up in RACF, and say, yeah, this guy's authorized, that guy's not. So it can offload some of the security work from ZOS to the Data Power appliance. Data Power provides, like I said, RACF access or SAF access, certificate service, private key service, and it works in hand with ZOS. Now the next technology we'll talk about is transport layer security. You probably know that as SSL. You know, when you go to your browser and it says HTTPS instead of HTTP, you know you're using SSL. It's traditionally a socket layer service. Now transport layer security is a TCP only because it requires reliable transport, and it's application-to-application security. It provides partner authentication. It provides encryption using different cipher suites. And on ZOS, there is a ZOS element called System SSL that's part of ZOS cryptographic services. It's not part of COM server. It's an element of ZOS that C and C++ applications can use to do socket secure layer. And there's also a Java extension. But to use these, you have to change your source code, right? You have to change your socket calls to specify SSL. Well, on ZOS COM server, we provide application transparent TLS, which means the stack will do that for you and the applications don't require any changes. And the way that works is we install the AT-TLS policies in the TCP layer, and when the client comes in that matches the policies, the TCP layer manages it for you. The TCP layer manages transport layer security, talks to SSL. So this is application transparent, so you don't have to encode it in your application. You specify in the policy which TCP traffic is to be protected, and we implement it all in the stack. So it's fully transparent, but it doesn't have to be. The application, we have optional APIs. The application can examine and manage AT-TLS if they want to, and it's available to all TCP applications, including CICS sockets, and all programming languages except Pascal. And the thing about it is we support all the standard configurations. ZOS as a client or server. We support both client and server authentication. We support SSL v2, SSL v3. We support all the current versions of TLS, including 1.2, which is added in v2r1. So it uses System SSL, the ZOS element, for SSL TLS processing. Now, the remote endpoint doesn't know I'm application transparent. It just thinks I'm a compliant implementation. So the main value of this is you don't have to implement it in your applications. You just use the configuration assistant to configure an application transparent TLS policy, and ZOS implements it transparently to the application. And here are a list of some of the many applications that use AT-TLS. Most of our communication server applications use it. DB2 uses it, IMS, JES, Tivoli, RACF, CICS sockets applications, third-party applications. Basically, anybody that does TCP/IP can use AT-TLS transparently to the application by configuring it with our policy infrastructure. Now, there are some advantages to this that may not be immediately apparent. The obvious advantage is you reduce costs, right? Because your application doesn't have to use SSL calls. You code your application just to straight sockets and then use our policies to use it. It gives you consistent TLS administration across all your ZOS applications. And this is the one that isn't necessarily clear at first, is you get access to new features with no incremental development costs. I mean, suppose you implemented SSL in the application. You said, I want to use TLS 1.1, code that in your application. Then TLS 1.2 comes out, and your partner says, I want to use TLS 1.2. But you now have to change your application. But with application transparent TLS, you don't. You just go into the policy, into the configuration assistant, you change the policy to say from TLS 1.1 to TLS 1.2, you install the policy in the stack, and it all happens for free. That also means that when new types of policies come out, new standards, new encryptions come out, we in ZOS keep up with it in System SSL and in AT-TLS, so you don't have to. So when new technologies come out, your applications don't have to be updated to support them. You just have to update your policies to support them. We also, System SSL, which is the ZOS element, we're always focusing on improving its performance. So if you have not already invested in System SSL, we highly recommend you use AT-TLS. It's cheaper. But even if you have, you should consider switching to AT-TLS so you won't have to do development work to keep up with changing standards. We do that for you in the platform. All right, the next technology is intrusion detection. Now, we use the word attacks on your system, but attacks can be intentional or unintentional. Somebody's got a bug, they got a runaway application, they're not meaning to bring your system to its knees, but they do because they're stuck in a hard loop getting sockets, something like that. So what is an intrusion? There's three types of intrusion. There's information gathering, right? Somebody's probing your system to find where are the open ports, what's the topology, where's the data. Also eavesdropping, impersonation, and theft. People try to get on the network and they try to grab information or to learn what's there. And then denial of service, which is attacks on reliability. Either a single attack, for example, an attacker might know that a certain OpenSSL stack has a bug that if you send it the right kind of malformed packet, it'll blow up, right? Or multi-packet attacks to flood systems. Those are all the kind of attacks. And they can occur from within or without, right? Firewalls, company firewalls, are not sure protection from attacks because remember, attacks can also be unintentional. Somebody might be developing something in your company network, have a bug, and flood your network, right? Or you could have insider attack problems. So company firewalls provide some level, but they don't protect from internal attacks. But also, you still have some access from the internet through a DMZ. So remember, attacks can be intentional or they can be as a result of errors. And we provide a wide range of technologies for intrusion detection and support. This is all managed through the policy infrastructure I discussed before. So we can block scans, we can block numerous types of attacks, we can block malformed packets, you can restrict what IP protocols and IP options people are allowed to use, you can restrict how ICMP is used, you can put in policies to prevent floods and queues backing up. We've got all kinds of attack types. We also have traffic regulations. You can use policy to limit, for example, how many connections a given client can establish. Say this client, you can have 10 connections and you can't have any more. That prevents floods. You can also specify how deep the data queues can get for UDP and TCP. When we detect intrusions, there's various actions you can configure. We can discard the packets, which is the most active method, which is basically, okay, you've had too many connections, I'm going to throw away the rest of your connections. You can limit connections, you can drop existing connections, or you can just log it. If you're testing it, you want to see what's out on your network, you don't necessarily want to stop it because it might be legitimate traffic. You can log it, examine the logs, decide if traffic is legitimate, allow it if it is, and block it if it isn't. We also can send notifications to external event managers, Tivoli NetView. We can send notifications there. So with IDS, we're broadening the overall coverage. It's not just we protect against this one attack. We protect your whole stack against a wide range of attacks. We detect statistical anomalies in real time. We keep track of what's going on in your system. We can control prevention methods on the target. So it's a very powerful, very widespread in-context protection. It's probably be worth an entire presentation on its own of how to use this. But the mainframe is very well protected, a lot of technologies, configure it through the configuration assistant using policy-based networking, without requiring changes to your code. All right, that's the end of the presentation. Hopefully we've given people a good high-level view.